Welcome to this video. We're going to work through some problems on the homework. First, let's skip to number 5. We have an Atwood machine, 2 masses connected to a frictionless pulley by a string. They are released from the position shown. Determine the acceleration and the tension in the string. First, we draw the forces on the objects. We're using G equals 10, so the gravity forces are easy. This thing is pulled down with M times G as the gravity force. That's 12 times 10. And the 4 kilograms is pulled down with M times G. That's 4 times 10, or 40. But the string has also been stretched out. Normally it's maybe this length. And this end has been pulled down to here, and this end has been stretched to here. So both ends are getting pulled back up with some tension force. There are the tension arrows. We're almost ready. Now we just have to decide on a sign convention. Where is the positive direction? We're used to saying that up is positive and down is negative. But that's a problem for this question. Here's the reason. This 12 kilograms is accelerating down, and the 4 kilograms is accelerating up. But they have the same acceleration because they're connected by a string. So if this is a positive acceleration, then the 12 kilograms has to have a positive acceleration too. We can't simply use up is positive and down is negative, because then the 12 kilograms would have negative acceleration and the 4 would have positive. So instead what we do is we say exactly what we just looked at. We say whatever direction the whole system is moving in, that single direction is the positive direction. So on the right side, the system is moving up. That's the positive direction. And then we loop around like this. That's the positive direction. And on the other side, the system is moving down. That's the positive direction. And we've just guaranteed that the entire system has the exact same value of acceleration. Okay. Next, we write down Newton's second law, F net equals ma. We are going to apply this equation to both of the two objects. We'll add the forces acting on the 12 kilogram mass and the forces on the 4 kilogram mass. But we have to write 2 equations because they're 2 different objects. Alrighty, here we go. For the first, let's choose this one as our first object. We've got the mg pulling down, but it's pulling in the direction of motion, so that's a positive force. Positive 120. And then tension is pulling up. That's against the motion, so that's a negative force. The mass of this object is 12, and the acceleration is a. Turning to this object, we have tension pulling in the direction of motion. It's pulling along this way, so that makes it positive T. And the other force acting is mg. That's pulling against the motion, so it's negative. The mass of the second block is 4, and it has the same acceleration a. These 2 objects have the same value because they're connected. Now we have 2 equations and 2 unknowns. We can add up the 2 equations. I'm going to add the left side here with the left side and combine it right there. Then on the right, I'll add the 12a, this side, and I'll combine it here, and I'll set them all equal. Okay, so I'm going to have 120 minus t plus minus 40, and then I have 12a plus 4a. So negative t and positive t, when they add, they make 0. So on the left side, I just have, I have 80 newtons. And on the right side, I have 12 kilograms times, I've got 16a. 80 equals 16a. I divide both sides by 16, and a comes to 5 meters per second squared. The 80 has units of newtons. This has units of kilograms, and a newton over a kilogram is a meter per second squared because a newton is nothing more Newton is nothing more than a kilogram meter per second squared. So we've taken out the kilograms. Next, we find the tension. To do that, we look back to one of the equations we said we wrote down before. I'll use this one. I'm going to plug in for A, because I know that now, and I'll solve for T, my unknown. Okay, so T minus 40 equals 4 times the acceleration, which is 5. The right side is 20. I'm adding 40 to both sides, and I get 60 newtons, and I've put a point there for sig figs. Which means, whoops, this should be 5.0 for sig figs. 5.0. Okay, number 6. We're going to do the same thing. The first step is to draw the forces. We have 240 newtons pulling down, and we have 70 newtons pulling on this one. There is tension. The tension pulls up right here, and it pulls up on this end of the string. We write down Newton's second law. Mass times acceleration. We apply the law to this block, but first we have to decide what's the positive direction. Well, 24 kilograms is bigger than 4, so the whole system is going to move and accelerate this way. That will be our positive direction. So 240 is positive, 70 is positive. Wait, 70 is negative because it's pointing down against the positive direction, against the motion. This tension is positive, it's with the motion, but this tension is against the motion of the system, so it is negative. All right, on this block, 240, that's one of the forces. Tension is the other, the mass is 24. And 240 pulls with the motion, so it's positive, but the tension is pulling against the motion, so it's negative. In the second case, for the second block, the mass is 7, but we again have 2 forces. So there's the 70, which is against the motion, pulling against, so that makes it negative. And then we have tension, which is pulling with the motion, making it positive. I add these two together. That's the simplest way to solve this system of equations. The tensions cancel out. 240 and negative 70. That makes 170. And I add the right side, getting 31a. When I divide, I get 5.48, or for sig figs, 5.5 meters per second squared. Then I take that acceleration value and I plug it back into one of these equations to find tension. Negative 70 plus tension equals 7 times the acceleration. And for the acceleration, I use the unrounded value, 5.483, ... I add 70 to both sides, and what do I get? Let's see, times 7, the acceleration times 7 plus 70, and I get 108, which rounds to 110, so that it has the correct number of sig figs.